Okay, guys, welcome to Part 2, Chapter 3, List Processing with CTA. We're going to learn how to do critical path analysis to create priority lists. But first off, I just want to do an example of how we would do a problem, go through each of the steps so that we can make sure that we're aware of it. So here's a problem, and I'm going to give you a priority list. It's a strange one. It's going to be backwards odds followed by the the backwards even followed by the forward odds. That's just the order of which I hereby declare everything to be important. So now I'm going to try to schedule this. I'm going to try to schedule this on two machines or processors. Sometimes I'll write M, sometimes I'll write P, but I'm going to do two machines. And here's my time marker at t equals 0. And I now create my available list at time equals 0. And I write down T1, T3, T6. Why? Because it's very clear that there's my available jobs. Now, since I have two people waiting at time equals 0, I must use the priority list. Now, the strange thing is the priority list says T6 is the most important, and T1 is the next most important, so I put them in, and they both run for 2 hours. And so, following what I did before, T6 and T1 are assigned, updated the priority list, updated the available list, put in my end times. Now I move my time marker forward. And so time is going to move to t equals 2. Now what happens at t equals 2? At t equals 2, both T1 and T6 end. Now when they end, that means T2 is available, and additionally T7 is available at time equals 2. Now, I have T3, T2, and T7 available, but only two people working. So again, I have to go to the priority list to determine which job does the people get. So amongst T2, T3, and T7, T2 is the most important. And amongst 3 and 7, 3 is the most important. I updated my priority list, updated my available list. Now I'm going to update my digraph by assigning T2 and T3. Now T2 runs for 3 hours and T3 runs for 3 hours. And again, I have this strange fact that they end at the same time. Now, it's not unheard of to have many jobs start and end at the same time, but that's just how it's working at the moment. Now, updated, updated, updated. Boss takes a sleep, and we move forward to time equals 5. Now, when time equals 5, T2 and T3 just ended, so I get to cross this out, and now I get to add on what's available. This is a slight subtlety. Even though an arrow went away from T5, there's still an arrow from T4. So I don't add T5 as available. But since T3 ended, there's now no longer an arrow to T4, so T4 is at the available list. So right now at time equals 5, 4 and 7 are available. 2 jobs, 2 people. I don't even look at the priority list. I just drop them in any order I like. T7, T4, doesn't matter. They just go in. 2 jobs, 2 people, no decision to make. Now, T4 runs for 4, and T7 runs for 2. So now, this is at 7 up there and 9 here. And it just got slightly interesting. So, updated, 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 updated. And now we move the time marker forward. And now the time marker hits 7 before 9. So at time equals 7, T7 finished. And so at t equals 7, T8 becomes available. Nothing else. And so if one person at time equals 7 waiting for one job waiting for one person just gets put in. Don't even think. T8, cross it out, cross it out. Doesn't matter. Now it runs for 2, so 7 and 9 would be right there. And so everything's been updated. I want you to notice that there's not many jobs left. T4 and T8 are now at time equals 7 running simultaneously. Now when we move time forward to t equals 9, T8 finishes, T4 finishes, and just like that, T5 is the only available job at time equals 9. You plug it in, it runs for 4 out to 13, and there's downtime. And so there's our schedule. Not bad. Is it good? Could have it been done better? Well, we're going to try a different approach to this. We're not going to write down just any old priority list. I'm going to put this guy back down. And now I'm going to ask myself, why did that schedule have downtime that we got? Why didn't we apparently get an efficient solution? And one of the reasons we can answer is we never considered the relationship that these dependencies have. These arrows say certain things have to be done. So I'm going to look at some paths. T1, T2, T5. And that is 5 of 9 hours in length. So when one person works here and one person works there and one person works there, it's going to take 9 hours no matter what just to do that path. Now this path is T3, T4, T5, and that's 11 hours. So no matter what, the best schedule we're looking at the moment is going to be 11 hours because this minimally takes 11 hours. And this one is just 6 hours. So I have reason to believe I might get a better schedule because our last schedule we got 13 hours completion time. And that's greater than 11. It seems like maybe we can hit that critical path. That would be nice. So how are we going to try to hit that critical path? Well, once I found the critical path algorithm is the following. CPA. Find the critical path. Write down the head. Cross it off. And now we repeat. So I'm going to use that here. I'm actually going to destroy this picture one more time. So my very first time through the critical path algorithm is I look at this and I go, here's the critical path, it's of length 11. I'm going to write down its head, T3. This is the beginning of my priority list. Now, write down the head, then cross it off. Now repeat. So now, this is no longer the list of the critical paths. They are 9, 8, and 6. 9 is the longest in this graph. T1 is the head, so I'm going to write it down. I'm going to cross this off. And now I'm going to repeat. 6, 8, 7. This is the longest path here. So I'm going to write down T4. I'm going to cross it off. I'm going to repeat. 6, 7. T2 is the longest path. The head of the longest path. Cross it off. 6, 4. This is the longest path. That's a path. It's just a task all by itself, but that's a path. T6 is the head. I cross it off. And now I have 4 and 4. Since they're tied, I can write either down or both. We have a notation. We can do it this way. We can write T7, comma T5, and we can brackets around it, which says humans can choose for other reasons why you might pick one over the other. We call these ancillary or auxiliary concerns. The math argument doesn't care which one of you put in. Either order is fine, but humans might have a reason. I mean, it could be that one machine has a habit of making a lot of noise and somebody doesn't want it running at a specific time. Who knows? So we're going to cross out the 7 and the 5, and that leaves the final task, T8. So here is a priority list. So now I'm going to copy this priority list down. And the digraph. And now I'm going to schedule again on these two, this schedule on just two processors. So here's machine 1, here's machine 2, and I'll leave that up there, but I'm going to make the available list. Now, at available list, at time equals 0 is not much different than what we did before. That group, T1, T3, T6. Now, since I have two machines waiting at time equals 0, between 1, 3, and 6, 3 gets assigned first. Between 1 and 6, 1 gets assigned next. T3 runs for 3. T1 runs for 2. And there's the beginning of my scheduling. Very different than the other one. Now, I've updated the available list, I've updated the priority list, I've put the end times in, I've updated the digraph. I now move my time marker from T equals 0 to where? Well, the next stoppage time, the person that wakes up the boss, is at time equals 2. So, time equals 2, something happened. Well, what happened? What happened is T1 finished by machine 1 having worked on, machine 2 having worked on it. And when T1 finished, a new job became available, T2. We are now at time equals 2. One job is running. One person is waiting, but two jobs are available. We need to pick between T6 and T2. So I go to the priority list and discover T2 is listed before T6. So I put it in. T2 will run for 3, so that'll bring it out to 5. And I update my digraph. I have updated my available list, I've updated my priority list, I've assigned in my digraph, I've got the end times in, I move the time marker forward. But now, time stops and wakes somebody up boss up at time equals 3. Why? Because machine 1 goes, hey, boss, I need a job. No machine is willing to wait. So T3 just finished. Well, when T3 finished, T4 became available. So one job is running at time equals 3, T2. Machine just finished. 2 jobs, T4 and T6, waiting to be assigned. I go back to my priority list because I have to make a decision, and between 4 and 6, I pick 4. Now, T4 just got assigned. 2 jobs are running. When does T4 end? 4 hours later. That's out till 7. I've updated my available list. I've updated my priority list. I've updated my diagram. I have my end of time markers in. I move time forward now to time equals 5. Now at time equals 5, what just happened? Well, machine 2 just finished task 2. So time equals 5. Did anything happen? And the answer is no. Because T5 has not become available. T4 is still running. It's circled, not crossed out. There's still an arrow going to T5. T6 has been available for some time. So our available list contains exactly 1 job. There's exactly 1 person waiting at T equals 5. No need to check the priority list. If you did, you discover, oh, 5 is the only thing on the list that I'm interested in. Sorry, 6. T6 is the only thing. I cross it out, and I drop in T6. So T6 has been assigned. Updated that, updated that. Oh, I've got to put my end of time marker in there. Oh, it goes right out to 7. Interesting. Okay. 2 jobs running. Let's take our nap. Who wakes us up at 7 o'clock? Why, both machines. Machine 1 and machine 2 finish. So at 7 o'clock, T4 finished. 7 o'clock, T6 finished. And now, at time equals 7, T5 became available. And T7 became available. Now, 2 people waiting, 2 jobs. I really don't have to look at the priority list. They just get dropped in. Now, it turns out they were equally important, but didn't have to worry about that. T5 and T7 went in. So, we assign them. We put the end of time markers. 7 plus 4 is 11. 7 plus 2 is 9. I updated that, updated that, updated that. Time to take a nap, and machine 2 wakes up the boss at 9 o'clock. Why? T7 is completed, and we have reached time equals 9. And that is the last of all jobs possible to be available. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 jobs. We've reached the end of really doing things. 1 person, 1 job. Don't worry about the priority list, but we're going to do all the updates. Runs for 2. 9 plus 2 is 11. Circled. And now when you move the time marker forward and wake people up at 11, everything is done, and this has completed in a wonderful way. There's no downtime for the employees. Both 2 employees work strictly straight through to 11 o'clock. And nobody can do this faster, because 3 plus 4 plus 4 is 11. This is the fastest any group of people can do it. This is optimal. That is really cool. It is optimal because we've finally reached a moment in time which we know, because of the critical path, that nobody can do it faster, even if they had 3 people. Now, the surprising thing is when you try to actually schedule with 3 people. So I'm going to take, and I'm going to do this, it's like the 4th time I'm going to write it down. I'm going to schedule this with 3 people, and you're going to see odd behavior. And here we go. I'm going to schedule this with 3 people, and you're going to see a frustrating aspect of scheduling when there's too many people there for the jobs. So first off, our available list, again, time equals 0, is T1, T3, T6. Weird thing is, 3 people at time equals 0, 3 jobs available. Don't even look at the priority list, drop them in. T1, T3, T6. Now, this is easy to do, but I want you to notice that T6 is a long way from the front of the priority list. Didn't have to use it, but they're only available. When we cross them out, you can see that the priority list is not being used in order, and it hardly ever is. It just happens. Now, T1 ends at 2, T3 ends at 3, and T6 ends at 2. So this is what it looks like with 3 jobs assigned to 3 people. Boss takes a nap, time marker comes forward to 2, and at time equals 2, T1 finishes, and T6 finishes. So time equals 2, T2 is available, and at time equals 2, T7 is available. And we have 2 people waiting, 2 jobs, no choice. They just get thrown in. T2, T7, T2 there, T7 there. What's their end of times? T2 runs for 3, 2 plus 3 is 5. T7 runs for 2, 2 plus 2 is 4. Updated, updated. Oh, I didn't have 2 yellow circles. I forgot to circle that one. There we go. And I forgot to circle this one. So now I have 3 running machines at time equals 2. This started, this one's still going, that started. All right, now we move the time marker forward from 2 to 3. What happens at time equals 3? Machine 2 woke up the boss because T3 just finished. Now when T3 finishes at time equals 3, T4 becomes available. That's it. Looks like we're scheduling really efficiently. Things are going great. 1 person waiting for a job at time equals 3, 1 job available, we assign it. T4 runs for 4, we're going to be out at 7. We highlight this. Now this is great. 3 things. Everything's running just fine. So, move time forward to T equals 4. At T equals 4, T7 just got completed by machine 3. And T8 became available. 1 person stopped, 1 person needed a job. Plop it in. T8 runs for 2, so that'll be at 6. Cross out T8, cross out T8, circle T8. It seems this is running just beautiful. 3 jobs, everything's working. We move time forward, so time equals 5. T2 is just finished by machine 1. but it finished something, but T5 isn't available. It still has an arrow coming to it. So at time equals 5, even though machine 1 finished, there's no available jobs to add. And there are no available jobs here. What has just happened at time equals 5, machine 1 has nothing to do. So machine 1 is going to be assigned downtime until the next stoppage, until something happens that can help us figure out what to do. So we're dropping in some downtime. Doesn't mean it's necessarily bad. We should call it idle time. Downtime is traditionally referred when something is broken. So we're going to put in some idle time. So machine 1 is idle. Nothing to update, nothing to update, nothing to update. Move time marker for the time equals 6. So now we just came up to time equals 6. Now at time equals 6, T8 just got finished by machine 3. Uh-oh. T8 just finished. There's no new things became available. Again, nothing to add to the available list. And now at time equals 5, we have two machines waiting for a job, and I can't give them anything. So they get idled to the next stoppage time. Nothing to update, nothing to do anymore. Move the time marker forward to 7. So now we're up to time equals 7. What happened at 7? Machine 2 finished T4 and woke the boss up. Boss observes that T5 is now available. 3 machines waiting to work. One job available. He just plops it in there, puts it anywhere he likes. Here's T5. It's going to run for 4. We're out to 11, and lots of downtime. But we finished at 11 o'clock, exactly the same time as we finished with 2 people. So does it make sense to have 3 people working on this if 2 people can get it done exactly at the same time? That's questions that might have a affirmative answer. Maybe these are permanent employees. You know, if you had put the 5 down here, you could send machine 1 and machine 3 home early. They're people. They might have been happy to have a short shift. Those auxiliary or ancillary concerns are not part of the mathematician's process. If you're forced to use 3 machines, you're still getting an optimal solution, but you have idle time. You can have some flexibility to move things around. It is difficult to schedule to make people happy, make the boss happy, get things done, and keep people working, especially when you have a forced situation. A very unusual fact arrives in scheduling. This unusual fact is sometimes idle time happens, such as here, yet the schedule is considered optimal because nobody can do it faster. However, if you compare it to the last time we got optimal, this one was just as fast, but there was no downtime. Which is more optimal? Well, we don't address that. For us, the question of optimality only deals with completion time as best as is possible. Now, there's one basic rule that a person can use for determining a good schedule. Rule 1. No idle time. Then this is machine number optimal. What does that mean? It means for the machines that you've put at, if there's no idle time, it's optimal. It may be possible to do it faster as a global. This is a local optimal. Think, for example, one machine running all the time, doing some jobs, and it finishes. There's no downtime, no idle, because he doesn't wait. That's, quote, a machine optimal schedule. And we just had one that looks like this. They finish at the same time. We could immediately say it's machine optimal. Rule number 2, though, is a global. This is a local optimal. Rule number 2 is a global optimal. If the completion time equals the critical path length, global optimal. That means nobody can finish earlier. This is machine optimal and globally optimal. This one is globally optimal. Wow, that does not look like a good machine optimal. And last but not least, there's one more practical rule. Let's suppose you've got a bunch of jobs and the total hours equals 120. Well, two machines should say, if you finish in 60, you're great. Nobody had any trouble. If you had three machines, 120 divided by 3 is 40. If you finish in 40 hours, that's great because no downtime, 40, 40, 40. But if you, let's say you had 7 machines, 120 divided by 7, and let's say no jobs allow for parts to it. I mean, to break it up, no decimals, everything's in even units. Well, does 7 go evenly into 20? No. So it goes in, 7 goes into 12 once, it leaves 50, 7 point something. So if 7 machines were running, it might be possible for this machine to hit 17, this machine to hit 17. It might be possible for 4 machines hit 17. 17 times 4 is 98. The 5th machine it's 5, 6 machines. Sorry. Forgot about 7 machines. We can have 5, 6 machines. All of them hit 17. 17 times 6, 42, 4, 6, that's 102. The last machine, or one machine, would have to go out to 18, which means that if we didn't have tasks divisible to a smaller amount of time, they have integral parts, this is a great schedule. You couldn't expect 7 machines to do less, because as soon as you move that one less, you haven't done all of the work. 120, you would have done only 119. So, if you do the total task times, total task times, divided by the number of machines, and then you round that up, if that equals your completion time, then you are machine optimal. You can't do better with that number of machines. And so here, total task times, 120. Divided by 7 machines was 17 point something. No matter what the number is, if it's a decimal, round up to 18. Did our schedule finish in 18? Then we would say this is a machine optimal schedule. Locally optimal. All right, that's now 2/3 of the way through Chapter 3.